All right. All right, Mr. TA. I got this big homework assignment due tomorrow about op amps. What even is an op amp? Can you please help me? All I got is these triangles on my piece of paper from class, man. I skipped the first 3 classes. I'm way behind. What is an op amp? Is this like Minecraft?
And yes, it's just like Minecraft, but
Just like comparators in Minecraft.
basically, it's just basically the same thing.
Can we just do it in Minecraft? Can we open up Minecraft?
No.
I don't learn like this. I'm a visual learner. I have to.
Hang on. All right. So the op amp is the premier linear device.
Premier.
Yes.
Like the head of state.
Basically. So this part, the plus, is called the non-inverting.
I don't care about the names, man.
No, listen.
It could be named Larry and Jeff. I couldn't care less.
Non-inverting. This part is the inverting.
Who cares?
You should care. It's the output. Boom. The op amp has a power source, external power source, and a negative external power source.
Does it have to be the same value? Here you have VCC twice. Does it have to be equal opposite?
Well, basically, yes.
It does?
Yeah. Basically. If you have two things connected to the input and the output, wouldn't you think that, well, there's current going in there? Current going in there and something coming out? There's a current coming out.
No.
Well, actually, in Minecraft, yes, you do. You have a current.
Well, you have an input and you have a on the side.
Yeah. But it's still the same thing. In Minecraft, it's still the same thing. You still instead of redstone, you have like some electric current kind of thing. So like one of the.
Yeah, but does the current come from the left or from the top and the bottom?
Okay. Here's the thing.
Please do.
One of the things that's going on inside this op amp, the current that goes into the op amp, well, is 0. And that is so there's an internal resistance that is so large that makes it so that the op amp doesn't draw current from the non-inverting or the inverting part.
It just takes the voltage values.
Basically.
It just samples the voltage values.
So one of the things that we have to understand,
just like in Minecraft.
But here's the thing. Here's the detail that Minecraft doesn't go into. Mm-hmm. The output characteristic, this output is essentially somewhere equivalent to, V out is equivalent to, we have some sort of, this is called a gain, op amp gain. And
it's a TP? What is this supposed to be? It's supposed to be an A?
So this is non-inverting, inverting. Those are the non-inverting voltage, the inverting voltage.
Oh, so, no. Is this stupid, like, semiconductor stuff again? NNP?
No.
I'm leaving.
No, it's not. No, it's not.
Good. Okay, good. It's mine. It's okay, good. Thank God.
Look. We're not going to do that stuff.
I would have left.
Oh yeah, left. Fair enough. But
if you tell me there's a transistor inside this, I'm leaving. If it's true, keep it a secret, please. If it's like a bunch of them, keep it a secret. I don't want to hear it. I don't buy that crap. It's just a myth.
Okay. Don't tell him.
Oh look, it's doped and it's got holes in it. That doesn't make any sense. Swiss cheese. I'm dropping out. If that's next year, I'm not dropping out.
Well, funny.
I'm going to civil engineering. Dude.
Whoa! Don't do that. Come on, don't do that.
You're right. Civil's even worse.
This is the characteristic of the output. But here's the thing about here's one of the interesting about this. This is like what we call this the open loop gain because this is not connected to.
Is this going to be a vocab test, man?
Yes,
all these words.
Yes, this is a vocab. No, it's like an implicit vocab test. It's an implicit vocab test. Basically, if you don't know the vocab, well, you're going to fail the test. And it's not like no one's gonna test you on the vocab. No, who cares? But it's like if you don't get what's going on, you're gonna fail. But this is important though because one of the things about this output is that this right here, this open loop gain, is really big. It's probably like actually I don't think it has a unit. I think it's unitless. Yeah, it's unitless. But what we have is like the gain is probably the lower side of the gain is probably this big, and it's usually bigger than that. So
10 to the S.
So you would find out this situation. Mm-hmm. So like if the inputs say that you have VP and say VP is like what is it like 4/3 volts. So that's it. That's VP, and
Mhm.
VN is like 0 volts. So what would your output be? It would be your output would be
That number's too big for my abacus. I can't calculate that.
yeah, basically. It would be
Goes up to 20.
so this would be like a bajillion.
Yeah.
And the problem with that is that this little thingy can't output a bajillion volts. So it would basically be saturated. It'd be saturated.
Oh, does it go to the max?
Yes, it would be the VCC.
Oh, why didn't you just say that?
Because I had to show you this.
You could have just said that. It goes to the max or the min.
Or yeah, exactly. If it's negative.
So if you don't have 1,000,000 volts, it only goes to like 6.
Yeah, basically. That's one.
So what's the point? It's the op amp, but it goes to like 6.
Yeah, I know. I see that. I understand that. When I was running this for the first time, I was like, "What's the point? This seems silly." Well, I mean, like it's kind of
It's
like
a comparator. It's a comparator that saturates. It makes sense. I get it now. Give me the test. Professor, I'm ready. I'm ready.
No.
I have the equation right now on my arm. I'm ready.
You have the equation. So the problem is that the output voltage is limited by your supply voltage, and so the problem there is that that's not very useful because
It is.
No. You said it's a comparator, but it's like,
Yeah, it's good.
but I mean, like we don't just want a comparator. We want more stuff.
I'm an advocate for comparators.
I mean, like, but we want more than that.
We do.
Yes, we do.
What else do you want? What else could you want?
Well, what we do is we want to make use of these op amps in order for like signal processing purposes.
Oh, boring.
It's not boring.
That's boring.
No, it's not. Like
what are you gonna process?
Well,
you process this with,
do you want
like waveforms and stuff?
you know the volume button on your computer? Boom, there you go. You need op amps.
It's not an op amp.
Yes, it is.
That's in software.
No. The software uses the op amps.
Nah,
Yes.
that's fake.
No, it's
fake
not.
news.
Oh, okay. I'm gonna do a little plot. So you understand that we have say, okay. So this is the VCC, and this is minus VCC. So if it's like, it's usually hit there, and it's usually hit that. You don't saturate it one way or the other,
Yeah.
but in a very, very narrow place, it's linear. So this is like really small. So, when we're using the op amps, we usually use it in linear mode. So we need to basically configure the circuit however way we're using it. For if you don't want.
That's what the R's are for. You basically make the voltages so you're in the linear range.
Yes.
Okay, we're done.
No.
Test. There's the test. Just V equals IR and that equation you showed earlier. This is it.
So I'm going to show you the nonlinear. Okay. So here's what you need to do. So if you were like taking electronics, hang on. If you were like a sadist and you wanted to do all that, transistor, it would kind of look like this. And you would have. And this would basically be the model. So you would have your plus and your minus, and this would be your V out. And this right here is what you would call a dependent source.
Where's the top part? Isn't there like 2 voltages that come in?
Well, no. We usually don't write that in the notation of the op amp. It's implied that there's a power source. So we don't have to worry about writing it over and over again. We just have to save the ink and all that stuff.
Oh, so where's the ground come from then?
The ground? Oh, this is a model like what we have here.
Oh, it's fake.
Basically it's fake.
Oh, okay, never mind. Keep going.
The point is, if you were like in advanced electronics or whatever, dealing with that crazy stuff, you'll deal with this. But we're not going to use this for the actual course or whatever. We're going to get to the easy part. So let's say you have the idea where like the linear range, this linear range right here.
Yes.
So like you have the VCC, A, basically like that.
Yes.
Now, if we divide it by A and divide these by A, we understand that VP and VN, in order for this to hold, it has to be like the difference has to be essentially around 0.
Oh.
In an ideal op amp,
This is why you were talking. It has to be 0. This is why you were saying that.
Yes.
It has to be 0 because otherwise you're after linear range. You hit the max
Yes,
and
and it's not.
yeah. Who cares? Okay, fine.
This is for
Yeah, I got
ideal.
it. Next.
Okay.
Lecture 2.
Yeah.
Fast forward. 8x speed. Let's go.
Okay. This right here, ideally goes to infinity as well. So that's the ideal op amp. So basically, the currents going in to here are going to be 0.
Yes.
How would you make it so that
Plastic?
no? How would you make it so that VP is equal to VN? Like, how would you ensure this relationship? You need to ensure this relationship so we have an ideal op amp configuration.
This is the feedback, right?
Huh?
You just put it back in there.
But what?
Yeah, I'll put it back in.
Oh yeah, you got it. It's called feedback. Yeah, you got it.
Yeah.
See,
Okay.
you get an A on the test. So feedback.
Yes. Put it in the grade book. I'm done. Can I leave?
No.
Do you have access to the grade book or just the professor?
Hang on. No. Okay.
Professor Jones, can I get an A,
I
please?
literally can't tell you my relationship with the grade zones because it would, people would, bribe me and stuff. So the answer is I don't have access.
I have $5. You have access now?
I'm going to show you this one example, and after you get this one example down, you're going to be like a pro. You're going to be like, you know everything. Circuit configuration. Now, the idea is, okay, so what is VO? So here's how VO do. So now we have IP, and IP is 0. So IP is 0. And we have IN. IN is 0 too.
Yep. That I get, because it has to be 0. It's just probing.
Yes. So how do we find the output? Okay, I'll tell you. It's easy, super easy. So what we have here is called a voltage divider because of IN equals 0. So if we just look at this part of the circuit right here, we would have VO to these resistors.
Okay, we're just comparing.
So no,
we're comparing the time varying value to whatever the output of the voltage divider thing is at the middle, and then the difference comes out to the V0.
So you basically got it.
Times the bajillion number you spoke before.
So we have R1, we have R2. This right here is Vn, because this here is Vn. That's Vn, and this is Vn. So we have Vn is equal to R2, R1 plus R2 times VO. So now we understand that Vn is also equivalent to VP. Now that is called what we just did is called ideal op amp constraints. So ideal op amp constraints demand VP is equal to VN.
Yeah, but this requires you to have it set up. I mean, you have to set up a certain way. You can't just assume.
Well, here's the deal. Like,
it has to be fed back in properly. Otherwise,
We kind of let's get to that point. Let's get there.
So in the lab, I would mess it up and it wouldn't work, but you would do it right.
So we know Vn is equal to V source. So now what we have here is we have V source is equal to. So here's the thing. In order for this to the reason why this can work is because the op amp is like delivering V out, and so that this relationship is ensured. So like you said, you don't want to talk about all the little transistors inside the op amps. So instead, we're going to basically all that stuff ensures this relationship holds.
Yeah, but the thing is, if you didn't have the right side of that triangle attached to the left side in some way, it was attached to some other random stuff.
What was that?
If the right hand side, if that wire at the bottom was just cut.
This one?
If there was no feedback of any kind between the right hand side and left hand side, you don't have a guarantee that.
No, it would saturate. It would just saturate.
You only get that 0 thing if you have feedback in an acceptable way. Yes. And not always are acceptable, because you could just feedback crap and it would not work.
Yeah.
So feedback, only certain things work.
Yes.
I get it.
So this would be.
I wish Professor was as good as you. You're so much better than him.
Your professor was. There you go. That's it, and that's how you do it. So. Yeah, so that's it. So this right here.
Hold on. There is this kind of So this is what kind of system is this? This is not like a summer. What is this? This is a.
This is what you would call a non-inverting op amp circuit. So basically, we have.
Just
Well, no,
here's the
look. So we have this. We have VO is equal to some gain times the input, which is the voltage source.
Yeah, it's just sort of scaling.
So this can be, well, it's so like it's greater. Usually you want this. So I'm going to show you the inverting amplifier.
It's okay, I get it. You have a voltage divider going to the negative, you have ground going to the positive, and the output going back. So yeah, it's easy. I got it. I'm an expert. Where's the test? Can I see the test?
Okay, I'll give you a test.
Click it right now.
Okay,
I want the final exam.
Okay, this is
I want your done examples.
I'm gonna give you the final exam
for the course, not for this some lecture thing. It's for the entire course.
Okay, this is your final exam.
Yes.
What's the expression for V out? Go. It's your final exam. Go.
The expression for V out?
Yeah, figure it out.
Okay, let's think here.
So how you doing? You want me to intervene? You know, come on.
Well, I don't remember any equations I've written down, but let me just think here. So if that's 0, you're telling me the Vn has to also be 0?
Well, if you want it to operate linearly, you basically have to have it be 0.
Is this linear?
Yes, this is a linear configuration. Yes.
So in that case, Vn is 0.
Yes.
0 and Vn is the voltage across R2.
What's In?
The Ins are all 0.
Yes. So where's the I going? Where's the current going? The current goes from here.
Mm-hmm. Yeah, but it doesn't matter. The voltage is still probed there. It has to be a 0 voltage at that point, right?
Yes, this is right here. The potential here
there's the current
is
is
0.
still voltage, right?
Yes, the potential right here at this node is an equipotential of 0. Yes, 0 volts.
So then the voltage at V0 is equal to the voltage across R2. The voltage drop across R2 equals the voltage at V0. Fact, yeah.
Yes, you're right. Yes, that's true. We're going to look at this node. This is node A. We're going to look at node A. So we know the current going in is the same as the current going out. So we know V in is the same voltage as VA. So we know that Vs minus V in over R1 over R2 is equal to 0. Because the currents are the same. Over R1 plus V out over R2 is equal to 0. So therefore, we have V out is equal to...
Now, where does the A come in? Does that ever come into this?
Okay. The answer is yes, but here's the deal. If I derive this with the A, what we're going to have is we're going to have a complicated circuit. So I'm going to show you. I'm not going to draw it from. I'm just going to show you briefly. I'm going to show you some of my notes. The effects of op amp gain. So this is we're going to do. What I did here in this example is I did an op amp analysis of the first problem. That is the non-inverting configuration. That's what we did. Yeah. And here's the A. So what we have here is
that makes sense. You just basically
is like so think about this. So R1 plus R2 is so think about this. We're doing a voltage divider with RO, and we're adding these resistances together because there's no current here. We can imagine like we can.
Oh, this is the R0 inside the magic device.
Inside the magic device.
Okay,
yes,
I get it. That's fine.
And so what we have here is this configuration. There's A.
Yeah.
So now if we keep doing algebra, we have this configuration where V out is an expression of there's A and there's the Vs and plus another expression for V out because of the feedback. Mm-hmm. So now if we do more math, do more algebra, we get the A right here. And now we take the limit as A goes to infinity. The limit as A goes to infinity of V out. We have A right here, and if we in an intermediate step,
yes,
we have the A right there, because So basically that 1 plus 1, and forget about that, And those two R0 and R1, they're gone.
Yeah, they're small.
So there, and if we keep going here, A to
So
infinity,
you divide, then you get R.
there.
Yes.
So
yes.
basically, in this configuration, this is this is the inverting op amp configuration. The A, as A goes to infinity, is eventually taken out. So this is why we can use ideal op amp constraints and we don't have to worry about the A.